Okay, now we have talked about basic ideas about perturbation theory in a quantum mechanical system. First, the system was undisturbed. Next, a charged particle went close by, and as a result of this, there was a slight perturbation. And now the quantum system will have slightly different or entirely new set of energy levels. This we have discussed. Now see what is happening in the case of nuclear physics is that you remember that nuclear physics is yet again a quantum many body system, right? Now there we have neutrons as well as protons. Okay, fine. Neutrons are chargeless, protons are charged. So overall the nucleus is charged, right? If I am talking about atom, then it can be uncharged. It can be, not always, but I am talking about nucleus, so this is definitely charged particle overall. Now if I am going to write the Hamiltonian, you remember the Hamiltonian of this entire quantum many body system. How do we write? Summation ij, right? Next,
qi qj.
First pi plus wij. Now here I am neglecting 3 body terms, 4 body terms and other terms. I am just taking only the 2 body interaction. Okay. Next what I did is the following. I considered only the single body term. If I consider like this, Ti plus Bi, so this is your one body term, one body, okay, 1b. Next I can write like this, Wij minus your Vi, okay, so here index is Ij. Now look, this is your two body term. Okay, or basically here we have a subtraction term and a two body term. This term is known as the residual interaction. Why? What I have done is that I have incorporated a one body potential and again subtracted it. Now this term is your two body term. So this entire Hamiltonian now I can write as H is equal to H0 plus say H1. Okay, so what is this? Is your H0 and this is your H1. Okay, fine. So this is the one body term H0 and H1 is the residual interaction. Fine. Now see the similarity. Now I am rubbing this part. Okay. Now, just like your previous scenario, where we have got an unperturbed system, an interacting particle, and then overall the effect of perturbation was small, and we did perturbation theory, we applied. Here, what is happening is that actual Hamiltonian is the sum of both generalized Hamiltonian. Now, suppose in this H0 we have got one body term. Suppose I am taking harmonic oscillator plus L dot S interaction. Everything, okay, that we normally do. This is what is over here. Harmonic oscillator plus L dot S term is there. And this is basically your residual interaction. Okay. Now, this nucleus quantum many body system, this will have actually energy levels like this, which is because of this H0 equal to H is equal to H0 plus H1. This is the actual energy levels. But what we do in nuclear physics is that we consider only this H0 normally. If you look into the textbook, you see cell model levels and all that, where harmonic oscillator and L dot S is taken. There is no mention anywhere of this residual interaction. Why? Because we are assuming that there is no residual interaction. This is first approximation. Basically, what we are doing is that we are doing a choice of this H0. Remember what is there in H0? Ti plus Vi. So basically we are choosing Vi such that this H1 becomes small or basically tends to 0. This is an approximation. This may not be correct. Now we have to check whether this approximation is good or not. Okay, so how we do that? See. So this is the actual physics. Remember, there will be questions in the examination regarding this. Okay, now, so this is the actual energy level. Now what is happening because of this H0, when we do the calculation, we get a different set of energy levels. Because this is due to your H0, right? And this is your actual. Actual means, what is actual? Actual means your experimental, where the effect of H1 is included. Now, when we take this, we use the harmonic oscillator plus L dot tester, we do the calculation, we match with the actual experiment, and after our best changes of taking H0 and L dot S and all that, we are still unable, if we are still unable to explain the experimental spectrum, then what will this mean? This will mean that this residual interaction is indeed present. Okay? So this is how we do things. Residual means whatever is remaining. See what was there previously? I have included in H0 basically T0 plus V0, and here basically Vij minus Vi is there. Now this is still positive, or this is finite. This is what I would like to say, not positive, finite. So remaining interaction, residual means remaining, all that and nothing else. Okay. Okay. Now look carefully. See, each of these levels, as I told you before, will have energy. Again, they will have angular momentum. Again, parity. Again, lifetime. Okay, and also electric and magnetic moment. Now, for the time being, let me consider only about energy, angular momentum, and parity. Now, you see, this nucleus is an isolated system. Okay, so the total angular momentum will be conserved. Again, we cannot have a wave function where different parity terms are there. So, two things important. We have to consider same angular momentum states and they have the same parity. Now, you must be asking, why am I telling you this? The reason is that this is the energy levels due to H0. Okay. Now, as a result of this residual interaction, H1, what will happen is that there will be slight change in these energy levels. This I have told you previously, right? There will be slight changes in the energy level. They will not remain the same. Okay, they will not remain the same. Now, what is the guiding factor to find the new energy level? The first thing is that there will be mixing between same J levels having same parity, and this is the result of this residual interaction. See, so this is your H0 and this one is basically H0 plus H1. And how do we get this? Basically, we will have to consider mixing between same energy levels having same parity. So this will be the result of this residual interaction. And this is, through this procedure, we will get this new H0 plus H1 and then we will compare this with our experiment. Okay. Sometimes we have to fine tune some of the terms of this, each of the terms, okay, so that we can get an exact match. So this is a basic idea about nuclear structure basic shell model calculation.